This is the fourth installment from my tutorials on using LCD displays with the Raspberry Pi. It builds on my previous 3 videos, so I recommend you watch them first. This tutorial will demonstrate how to control an LCD display using I2C. We'll start with the PCF8574 I/O expander chip. First, I use sudo apt-get install python smbus to get the Python library for I2C. I'll also install the optional I2C tools, which has some very helpful utilities. The modules file located in the SE folder will need to be modified. I use sudo nano for editing and append I2C-dev and I2C-BCM2708 to the end of the file. After saving the modules file, it's necessary to reboot the Pi for the changes to take effect. Before getting into LCD displays, I want to quickly demonstrate how you control output pins on an I2C chip. First, I import SMB bus module, then instantiate an SM bus. I pass in the bus number, which is 1 on newer Pis, but can be 0 on the older revisions. I declare the address of the I/O expander chip in hex. I'll show you how to set and get the address later. A byte is comprised of 8 bits. A bit can be 0 or 1, and can be thought of as a numerical representation of an on-off switch. There are 256 possible combinations of bits in a byte, so I'll loop from 0 to 255 to show them all. I use the write byte method to send the byte to the chip and print it to the console in both decimal and binary format. Okay, let's run the program. You'll notice now that the LED light patterns match the byte patterns in the console. 1s are illuminated and 0s are off. The first column of numbers on the left are the base 10 numbers. These are the numbers which we use in our everyday life. And to the right are the base 2 or binary equivalents. This is the format that computers use to store numbers. You may have noticed a tilde in front of the byte variable. This is the Python unary operator, which inverts values, 0s to 1s and 1s to 0s. The PCF8574 pins cannot source enough current to drive an LED, but they can sink enough current. Therefore, I have the LED anodes connected to 3.3 volts and the cathodes to the PCF8574. When the pins are low, the LEDs light up, and when the pins are high, the LEDs go off. Just so there's no confusion, a 0 bit sent to an I/O port turns off the I/O pin to 0 volts, which is considered false or low, and a 1 bit turns on the pin to 3.3 volts, which is true or high. The cool thing about sending bytes is that you can change 8 pins at once with one command. The PCF8574 is an 8-bit chip. It has a port of 8 I/O pins labeled P0 to P7. To wire it up, we first need to assign a unique address to the chip using the 3 address pins labeled A0 to A2. Setting them all low equates to hexadecimal address 20. The LCD display control pins RS and Enable are connected to P4 and P6 respectively. The LCD data lines D4 through D7 are connected to P0 to P3. By the way, my pin selections were chosen to facilitate filming. You could use any combination you like as long as you specify the correct parameters in your code. VCC is connected along with the SDA and SCL pins, which are the serial data and serial clock lines. These are responsible for the I2C communications. On the breadboard, I have a PCF8574. I connect the ground pin to the ground rail, which is common to the Pi. I'll ground the 3 address pins to set the hex address. Each expander on the I2C bus requires a unique address. I connect P4 to RS, P6 to Enable, P0 to D4, P1 to D5, P2 to D6, and P3 to D7. Since the 3.3 volt SDA and SCL pins line up on both the Pi and the expander, I'll use a 3-pin jumper to connect them. That's all it takes. We can now control the LCD display, and we are only using 2 GPIO pins on the Pi. The I2C detect utility will let us know if everything is connected properly and will also show the hex address. The last parameter is the bus number. Again, on older Pis, this would need to be 0 instead of 1. The map shows that there is one I2C device at hex address 20. Now the question is, how do we control the LCD display from Python? If we import the Adafruit car LCD module and run help on the init method, we can see that the constructor takes an optional GPIO parameter. By default, it assumes the LCD display is connected to the Pi's GPIO, but we have the option to specify an alternative. Inside the Adafruit car LCD folder is a module for an MCP I/O expander, which is an alternative to the PCF8574, which I chose because I had them in my parts drawer and they are very easy to work with. The Adafruit module specifically supports the MCP23017, which is a 16-bit expander, and the MCP23008, which is an 8-bit expander and similar to the PCF8574. Unfortunately, there's no support provided for the PCF8574. Let's open the Adafruit Car LCD module and see what's required to implement a GPIO. I'll do a search for all occurrences of GPIO. Looks like we need a set mode method and a BCM property, also a setup method and an out property, and finally an output method. That's only 2 properties and 3 methods. I created a new Python module and imported SMBus. There is a class called PCF8574GPIO. I declared the properties BCM and out. I've created a skeleton for the 3 necessary methods: output, set mode, and setup. For set mode and setup, I'll use the Python pass statement because neither method is relevant. All pins will be output and numbered by their port numbers, which I can handle in the class constructor. For output, only 2 lines are required. I take the pass parameters and modify a byte representation of the I/O port using a function called changeBit. Then the SMBus writeByte method is used to write the modified byte to the I/O expander. Now I'll paste in the _init method, which is the class constructor. It fires when the class is created. A bus is instantiated, an address variable is declared, the chip is cleared by setting all pins low, and a byte variable is declared to hold the state of the 8 I/O pins. Next, I'll paste in the changeBit method referenced in the output method. This code might be confusing if you haven't worked with bitwise operations, which is outside the scope of this video, but basically the method just replaces a specified bit in the byte variable with the new value. Finally, I paste in an optional cleanup method to reset the pins on exit. That's all it takes. We now have a GPIO module for the PCF8574 that's compatible with the Adafruit LCD library. Back in idle, running as root, I import the Adafruit Car LCD module. I import the PCF8574 GPIO module that I just created. I instantiate a GPIO and pass in the bus number and the hex address. I create variables for the LCD display pin mappings. These correspond to the P-numbered pins on the PCF8574. I instantiate an Adafruit LCD where I specify our custom GPIO for the PCF8574, clear the display, show some text, and end up with the cleanup call. Now let's save and run the program. On the breadboard, the text is displayed on the LCD. The great thing about I2C is that you can daisy chain devices. We can add numerous devices while only using up 2 GPIO pins. For example, suppose we want to add a second LCD display to our Pi. For starters, we just extend the SDA and SCL lines to a second PCF8574 chip. Then we specify a unique hex address. I'll set A0 high by connecting it to 3.3 volts and leave A1 and A2 connected to ground, which is low. This equates to hex address 21. On the breadboard, I have a second display and a second PCF8574, configured similarly to the first. I changed A0 to high to ensure a unique address. I connect the 3.3 volt power, I connect SDA, and I connect SCL. That's all it takes to add additional I2C devices. Back in terminal, the I2C detect utility confirms that everything is working and shows that we have I2C devices at hex addresses 20 and 21. I'll add a second GPIO, but this time I'll specify hex address 21 for the second PCF8574. I'll also add a second LCD and pass GPIO 2. Put some text on the second display, and then clean it up. There you go. 2 LCD displays being controlled from Python using I2C, and only 2 Pi GPIO pins are necessary. I was going to end the video here, but after filming I serendipitously found some MCP23008 chips in my desk drawer, which I figured would make a good addendum. The MCP23008 has 2 additional pins, and the ordering is different, but the wiring is nearly identical. The only difference is that the reset pin must be pulled high by connecting it to 3.3 volts. In the Python code, I import the Adafruit MCP230XX module instead of the custom PCF8574 module. Instantiate a GPIO using the Adafruit module. The parameters are 1 for bus, hex 20 for address, and 8 for the number of I/O pins. The rest of the code remains the same. This is a great solution because Adafruit already provides the necessary support for the MCP23008. On the breadboard, we've got text. You might have noticed that there was a substantial amount of lag while the text was being displayed. This is one downside to the Adafruit MCP module. It's not coded very efficiently, so writes to the LCD display are relatively slow, which could be a drawback depending on the application. I looked online, and the majority of the I2C displays that I found use the PCF8574 chips. The rest, including Adafruit, use the MCP chips. But it's a good idea, before you buy, to check which model is provided. This tutorial was a viewer request, and any additional videos will be audience guided, so please comment what you'd like to see. You can support this channel by subscribing. Thanks for watching, and please check out my website, rototron.info.